Okay, so I am presenting on electrons as waves, and this is from 3.6 to 3.5 to 3.6. And so I decided to do this in my classic format as a survival guide to understanding things, which in this case is electrons. Um, so the first thing My first tip is to make sure you understand boring models and other paraphernalia. So, you know that feeling when you were just sitting in chemistry and you thought you understood things and you thought chemistry was easy, but then after you learn that electrons really aren't what you thought they were, you kind of are stuck in this quandary and you're just kind of confused. Well, you are not alone because I too had that moment, but you just kind of have to push through it and realize that there's other ways of looking at things. And we're going to learn some of those other ways other than the Bohr model. The Bohr model had some inaccuracies and some things that it, it couldn't necessarily explain. And so this is where we are going to get into tip number two. And tip number two is never forget your broccoli and do your planks. So Louis de Broglie, he is just a really smart dude, and he developed an idea about the stability of electrons based on another idea about electrons behaving like waves along with behaving like particles of matter. So most of the time, we refer to this as the dual nature of electrons. So essentially, it can act both as waves and particles of matter. And so it's really interesting. And the way I remember that is Louis de Broglie, sounds like broccoli, and so I have broccoli in there, and we have some waves down here, so just little ways to remember. Um, there's just one slight caveat, we cannot forget our Plancks. So de Broglie recognized that because an electron can behave as a wave, its energy and its wavelength are inversely proportional to each other. And because of the kinetic energy of an electron is related to its square of speed and mass, we can turn all of this into an equation called the de Broglie equation. And so we have our wavelength here, and we have Planck's constant, and we have the mass, and we have the speed. And so we have all of these components. Planck's constant is super important, and that is 6.6260700 forward 6.63 times 10 to the negative 34th meters squared kilograms per second. And so, depending on the question you're given, you might want to change this or convert it into different units. So just pay attention to like the meters or like the kilograms or the seconds. And so if like a question's asking for grams, make sure you convert that to grams. So you just have to be careful. Um, yeah, so there's more to this. So de Broglie did not stop there. He put into definition standing waves, nodes, and matter wave. So I just cut these definitions from the book, and I think they explain things very well. Um, a standing wave is a wave that oscillates back and forth in a fixed space, contrary to the way waves of light travel through space. So it's kind of like a instrument string. If anybody plays an instrument, it when you pluck it or if you draw your bow across it, like the string moves back and forth, it oscillates. And it can never really go more outside of the space it's in. It's pretty confined to the little section of space that it's in. Um, and a node is a location on a standing wave that experiences no displacement, or in other words, when electron density goes to zero. A matter wave is the wave associated with any moving particle. So, just pretty much basic definitions. Um, the next tip is doubt your doubts before you doubt Heisenberg. Yeah. Um, who likes to have principles about being uncertain? Apparently, Heisenberg does. And the Heisenberg principle, um, it's a little confusing because you're calculating uncertainty, which sounds a little counterintuitive, but um, Heisenberg addressed the questions about the locations of an electron, which is to essentially say that we can never ever know the exact location of an electron. It's slightly confusing, and the reason why we do it is so that we can understand the limits that we have as humans in this vast universe. Um, Basically, his uncertainty principle is delta x times m times delta u equals h over 4 pi. And again, the delta x refers to the uncertainty of the electron's position. The m relates to the mass. Delta u is the uncertainty in velocity. And h is, of course, Planck's constant, which again is 6 point, let me go back and double check. I should have this memorized. 6.63 times 10 to the negative 34 meters squared kilograms per second. So that is how you calculate the uncertainty of an electron's position. Tip number 4 is to stay away from mechanics, especially surfer mechanics. So quantum mechanics. At first I was a little confused by this subject because it just was confusing, but if being able to describe electrons as waves in words wasn't enough, we still need to learn how to describe them as numbers. So we do this with wave mechanics or quantum numbers. And so you can thank Schrodinger for this because basically he came up with the numerical fundamentals behind all of this by describing electron waves. Electron matter waves can vary with time and location. So the solution to this is wave functions. Um, Essentially, just don't trust surfer mechanics, wave mechanics. Yeah. So anyways, the square of a wave function is the probability of finding an electron within an atom, and that is basically what we call an orbital. So the wave function is describing electron matter waves that vary with time and location, and that is what a wave function is. But when we talk about the probability of finding an electron within an atom, or if we're talking about orbitals, that refers to the square of a wave function. And so they're two different things, but they still relate to each other. The next thing that we are going to talk about is quantum numbers. And quantum numbers are one of 4 related numbers that specify the energy, shape, and orientation of orbitals in an atom and the spin orientation of electrons in the orbitals. And so they actually have letters, and they are n, which refers to the principal quantum number, and then we have L, which refers to the angular momentum quantum number, and M sub L, which relates to the magnetic, I'm totally spacing here, the magnetic quantum number, and we have MS, which relates to the spin quantum number. And so all of these are different, and they all mean different things in reference to the location, the spin, the momentum, and a whole bunch of other things that we need to know when we're talking about electrons and where they are in an orbital. And to start out with, the principal quantum number, which is n, is a positive integer that indicates the relative size and energy of an orbital or of a group of orbitals in an atom. So, essentially, you can pretty much pick any number from 1 to infinity, and it can tell you what the size and the energy of an orbital or a group of orbitals in an atom is. And so the further you go out, the higher the orbital or the higher the number, essentially the higher the energy of that orbital, if that makes any sense. And in other words, we are talking about the shell. So you have your atom and you have your shells and in these orbitals. And so you're going to essentially, and you're talking about a certain electron, and you're going to essentially try and find that electron. And if you're the first place you're going to want to look is the shell. It's kind of like trying to find someone based on their address when you're mailing something or something, you know? And so you're going to ask yourself, what shell is the electron in? And so the principal quantum number answers that question for us. It helps us figure out what shell the electron is in. And so next, we have the angular momentum quantum number L. And so this one's a little bit more tricky just because you have to kind of think about it a little bit differently. And so this one is an integer with a value that ranges from 0 to n minus 1. And so for this one, you can pretty much choose any number from 0 to n minus 1. So if your n value was 5, if you were in shell 5 or orbital 5, then you would have to choose for your L value 0 to n minus 1. So it would be 0 to 5 minus 1, which is 4. So your L value could be 0, 1, 2, 3, or 4. So you have 5 possible values. Yeah. And so this one tells us about the shape of an orbital, or in other words, the subshell. And so you're in the shell of your orbital, and now you're trying to find in that shell where the electron is. And so the angular momentum quantum number takes us a step further to the location of the electron by telling us what subshell and the shape of the orbital it is in. The quantum number L has values and more letters that identify the angular momentum of an electron. So by this, when we are talking about the numbers 0, 1, 2, 3, 4 that it has, or the 0 to n minus 1, that was just in the example, we can correlate that with a letter, and that will kind of tell us what shape. Each letter has a different shape that it creates. So like you have s orbitals, p orbitals, d orbitals, or f orbitals, or g orbitals. And so if you have the shell, your n equals 5, right? And so you have 0 to n minus 1. So you have 0, 1, 2, 3, 4. When L equals 0, it is S. When L equals 1, it is P. When L equals 2, it is D. When L equals 3, it is F. When L equals G, it is 4. So basically, it's pretty straightforward and it's not too complicated. You just have to kind of memorize what L can correspond with, and you just have to memorize the ranges of the numbers and also understand what L can tell us, what the angular momentum quantum number can tell us about where the electron is and what it tells us about the orbital it is in. So it can tell us the shape of the orbital and it can relate us to the subshell. The magnetic quantum number, m sub L, so this is an integer value that ranges from negative L to plus L. I can't read that. So our shell was L equals 5. N equals 5. Okay. Our L value could have ranged from 0, 1, 2, 3, 4. So now our integer value it ranges from negative L to positive L. So it can be -4, -3, -2, -1, 0, 1, 2, 3, 4. So essentially, you have like 9 of possible things you can choose from in that. And so you have this vast range. And so this number helps define the orientation of an orbital and the space around the nucleus of an atom. And so knowing this, we get a step closer to finding the electron or kind of pinpointing where it is in the atom. And so that brings us to the spin quantum number, m sub s. So this has two values that it could be. So it's very simple. It's -1 or positive, -1/2 or +1/2. So it can either be two of those. It can't be both of them. Has to be one or the other. And so this quantum number tells us what the spin orientation of the electron is. And so it can be going one way or it can be going the other way. It can't be going both ways because that's just not how things work. Um, so I really want to kind of just like emphasize what this means. So a quantum number helps us identify the energy, shape, and orientation of an orbital in an atom. And the one thing that like stuck with me when I took chemistry before this class was an analogy that my teacher told us that we are kind of like the mailman and we're trying to find the address of this electron. And so this might be this country that the electron's in. So the orbital is like the country it's in. So we're going to the country, yeah? And this tells us this tells us which country in the world it is in. And then we have the angular momentum quantum number L. And this is like the state. So let's say we go to Utah, right? And so we get one step closer to finding the orbital and figuring out where the electron is. And then the magnetic quantum number, m sub L, is like going to the city. So Provo. So now we're in Provo and we get one step closer to finding the exact pinpointing where in space this electron is. And the spin quantum number is like, I don't know, the address. So wherever you live, so like maybe you live somewhere in like BYU campus, so you like maybe live in Heritage or something, or like Helaman. So it's kind of like that. And you get a step closer to finding it. And there's some other things that are of note when we are talking about orbitals and we are talking about quantum numbers. So the nth shell has n subshells. So if you have n equals 5, then the fifth shell has 5 subshells. If you have n equals 4, the fourth shell has 4 subshells. If you have 1 equals n, then the first shell has 1 subshell. So it's not super complicated, but just takes a little bit of practice identifying what it is and just kind of remembering these tricks. The nth shell has n squared orbitals. So let's say we're in the fifth shell, then it has 25 orbitals. And so let's say we are in n equals 4. We're in the n equals 4 shell. Then the fourth shell has 16 orbitals. Okay, and then each subshell has 2l plus 1 orbitals. So let's say that we are in n equals 4 and our L quantum number is going to be 3. So the third subshell has 2l plus 1. So 2 times 3 plus 1 is 7 orbitals. So shells have orbitals and then subshells have orbitals. Just things to kind of think about and try not to get confused on. So tip number 5, exclude poly. he can take it. So the Pauli exclusion principle is just kind of important, and it states that no two electrons will have the same set of quantum numbers. That's really all there is to it. So let's say you have, even if you have n equals 5 and for 2 electrons, and then you go on to say that the angular momentum quantum number L is 4, and they both have 4. And then you say that the magnetic spin quantum number is I don't know, 0. And then you go down to the spin of m sub s. They won't ever have the same, because at that point they would either have to have negative 1/2 or positive 1/2, and both of them cannot have positive 1/2, and both of them cannot have negative 1/2. It has to be either or. And that's really all there is to that. Okay, so now we're going to work on some practice problems. And so these are just from the problem set 7 that we did closer to the beginning of the year, but they never hurt to review. So the first practice problem is 1. Louis de Broglie correctly postulated that matter has wave-like properties. What was the de Broglie wavelength of the baseball? 0.145 kilograms thrown at 108.1 miles per hour, or in other words, 48.325 meters per second, by Nolan Ryan in 1974, the fastest pitch ever recorded. Okay, so for this one, you will essentially take the de Broglie equation that we talked about in the slides previous, which is the wavelength equals Planck's constant all over mass times the speed. And so in this case, we have Planck's constant, which is 6.626 times 10 to the negative 34 joules times second, and our mass is 0.145 kilograms, and our speed is 48.325 meters per second. And so you're just going to plug all those numbers in, and you should get 9.46 times 10 to the negative 35 meter. So essentially, let me see if I can write this out. So your equation is going to be that wavelength is going to equal dh over m times velocity. And so in this case, your h is here. That's going to be the Planck's constant. Your m is here. That is going to be here. Your velocity is here, and that is going to be here. And you're just going to calculate for your wavelength. And again, you should have gotten 9.46 times 10 to the negative 35th meters. And remember, wavelength is in meters. Sometimes it helps just to know what meters you're trying to get to. So in this case, it's meter. It's just going to be meters. So next, we are going to work on B. Assuming the uncertainty in the measured speed was 5.5 times 10 to the negative 28 meters per second, what was the uncertainty in the ball's position as it passed the hitter? The fact that the baseball had wave-like properties adds significantly to the challenge of hitting that baseball. So we are going to write this out. I'm going to write the equation. So our equation is delta x. Let me change my pen. Okay. There, we should be good now. Delta x times m times delta is greater than or equal to the h all over 4 pi. Okay, so in this case, we're going to want to rearrange the equation. So we are going to want to isolate the delta x by dividing both sides by the m delta u. And so to do that, we just all over the 4 pi, and we just put this in the denominator, and then we just solve like we did, we just plug in for the values. And so in this case, our h is Planck's constant, which is 6.626 times 10 to the negative 34th joules times second, and our m value is going to be 0.145 kilograms, and our delta U value is going to be 5.5 times 10 to the negative 28 meters per second. And so the answer you should get once you plug all that in is 6.6 times 10 to the negative 7th meters. And so with that in mind, if you compare the 6.6 times 10 to the negative 7 meters, our answer is going to be no. Okay, so now to the next problem. Practice problem number 2. What are the possible values of quantum number L when n equals 4? So when L equals 4, we can have from the range of 0 to n minus 1. So it can be anything from there. So it can be 0, 1, 2, 3, and 4. Okay, and so we essentially have 1, 2, 3, 4, 5 possible values. And they're 0, 1, 2, 3, 4. So which are the possible values of m sub L when L equals 2? And from here, our possible values can range from n negative L to positive L. Okay, and so we can have negative 2, can have negative 1, can have 0, can have 1, positive 1, and positive 2. So we can choose 5 values. We can pick from any of those, and that's the range. Our next one is going to be practice problem number 3. And it states which of the following sets of quantum numbers n, L, m sub L, and m sub s are actually possible. So we're just going to want to go through these and figure out based on what we're given if we can figure this out. So the first one, n equals 3. Is that possible? Yeah, you can have n equals 3. It's a positive integer. That works great. The next one is L equals 2. Does that fit in with our range from 0 to n minus 1? Well, that's 3. N minus 1 would be 2. So yeah, that works fine. Negative 2, again, that ranges from negative L to L. Negative 2 is in that range. So that works great too. That checks out. And here, can we have a positive 1/2 and a negative 1/2? Yeah, we can either have either or. So right here, it's a positive 1/2. And so that one works out great. So A works. This one, can we have n equals 1? Yeah, n equals 1 is fantastic. Can we have L equals 1 though? No, because that has to range from 0 to n minus 1. And in this case, n minus 1 would be 0, so it would be 1 minus 1. So that is not possible. So this one does not check out. The first one is n equals 1. That works great. L is 0, yes, because that is n minus 1, which gives me a 0. That has to range from, we can't because it has to range from negative L to positive L, and 1 is not from 0, so that one does not check out. There's this one. Does this one check out? No, because n cannot equal 0 because it has to be a positive integer, and I'm pretty sure that 0 is not a positive integer, so that is not a thing. N equals 2 can work. Great. L equals 0 here, and that ranges from 0 to n minus 1, which would be 1, so that works great. But our m sub L does not check out so well, just because 3 cannot be m sub L because that has to range from 0, so that does not work. So that one doesn't check out. So our only answer in this case would be A. Okay, so just to kind of recap, the important takeaways are just remembering the equations and what everything refers to, how everything relates to each other. So delta X refers to the uncertainty of the electron's position, m is the mass, delta U is the uncertainty and velocity, and h is of course Planck's constant. And remember Planck's constant. You don't necessarily have to memorize it, but just know what it is and how it is used. Just remember kind of things like that, and this is super important. And knowing how the energy and wavelength are inversely proportional to each other, and the kinetic energy of an electron is related to its square of speed and mass. And so how that all became an equation is super important. And again, just knowing the quantum numbers is really important. So just kind of going through and remembering everything, and you'll do great. And that is the end of my video.